Hi students, welcome to my lectures on thermodynamics. In the last class, we have discussed about the polytropic process. In today's class, let us concentrate on adiabatic process. And it is a special case of polytropic process. And in fact, you need to understand, the adiabatic process in a good way so that in future, when we are going to apply the adiabatic process for many different cases, so that you can able to distinguish what is the importance of the adiabatic process. And before I start, let us see these two diagrams. In addition, there is a piston and cylinder, and I have drawn some dashed lines and over the cylinder. This is called insulation. The reason for insulation is no heat can enter into this system. Before the process, because we are taking the system from state 1 to state 2 without putting some heat into the system. And in fact, why anything to get expand? Because if you see this state 1 to state 2, expansion happens. What is the reason for expansion? Have you ever thought? Because if you supply some amount of heat to the system, the internal energy rises, and this internal energy converts into this expansion work. In the adiabatic process, we don't supply any heat to the system. That means, why the expansion happened? Because this system already have its sufficient internal energy. Because of this energy, you can see if I remove these stoppers, because example, if the system has some P1, V1 and T1, pressure, volume and temperature. These are the latches. If I remove the stoppers or latches, if you remove the stoppers, it will get expand. Why it will get expand? It has some energy inside in it in the form of internal energy. This internal energy will cause some expansion work. That is what the beauty of the adiabatic process. Without supplying any heat, the energy contained within the system has expanded. And at what cost? Because if you can measure, generally you can measure internal energy depends on the temperature of the system. You can see P1 is the pressure, V1 is the volume and T1 is the temperature. After the expansion, P2, V2 and T2. Here, because it has expended some energy for this expansion, the temperature, the system will lose the temperature once it go from state 1 to state 2. That means temperature of the state 1 will be always higher and the temperature at the state 2 will always lower. Why it is lower? That means some energy has been spent in the expansion process. Because as you know, the first law states that the energy remains the constant. And if it is expanded, at what cost it has expanded? It is losing some internal energy in the form of work. That is why this is the beauty of the adiabatic process. So let us come back to the board. So I am taking the system from state 1 to state 2, which is expansion process. It has followed some path. This path is called adiabatic path. You can see in the last class we discussed if it is a polytropic path process, PV power n equal to constant, which is a polytropic. If you have to take it as a adiabatic case, the n will become gamma, that is PV power gamma equal to constant. What is this gamma? For the special case, for the ideal gas conditions, you can calculate the gamma by Cp by Cv, that is specific heat capacity at constant pressure divided by specific heat capacity at the constant volume. If you know the Cp and Cv of that particular ideal gas, then the ratio between these two, you can calculate the gamma. In general, based on the many researchers found out that the gamma equal to 5 by 3 for the monoatomic gas, gamma equal to 7 by 5 for the diatomic gas. If you consider only monoatomic gas, PV power gamma is nothing but gamma is equal to 5 by 3. That means PV power 1.66. 5 by 3 means 1.66 equal to constant. So when polytropic process is equal to gamma at special case of 1.66 for the monoatomic gas. So let us apply the formula in calculating the displacement work and temperatures, initial temperature, initial pressure, initial volume, and final temperature, final pressure, and final volume. Okay, displacement work is equal to P1 V1 per gamma by n minus gamma minus 1, because now it is a adiabatic process, into V2 power 1 minus gamma into V1 power 1 minus gamma. How this equation got, if you go to my earlier lecture, I have derived how I got this formula. So using this formula, let us calculate what is the displacement one in this expansion process which has done adiabatically. So here the P1 given 1000 Pascal, V1 is 1 meter cube, V2 is the 2 meter cube, and gamma which is 1.66. If you substitute each and every value in this formula, you get displacement work is minus 556.24 joules. I told you, right, minus, of course this is an expansion process. Expansion means system has something to the surrounding, done some work towards the surroundings. So that is why you get minus symbol. So this is the work spent. What is the final pressure? I use this small formula, P1 V1 per gamma equal to P2 V2 per gamma, because it's an adiabatic process. From this, P2 equal to P1 into V1 by V2 per gamma. If I put all the values, then the final pressure is equal to 316.43 pascals. If the initial pressure is 1000 pascals, the final pressure is 316.43 pascals. So now I have all the information, P1, V1, okay, P2, V2. Let us calculate the T1 and T2, okay. What is the initial temperature and final temperature if the cylinder contains 1 mole of gas and universal gas constant value is 8.314 joule per mole Kelvin. That means inside this 1 mole of gas is there. After expansion also 1 mole of gas will be there, okay. If that is the case, what is my T1 and what is the T2 during this expansion process? I know P1, V1, N1 number of moles are constant. Now because I said that this is a special case of ideal gas, I can use the ideal gas law. P1 V1 is equal to N1 R T1. From this, T1 is equal to P1 V1 by N1 into R. If I substitute all the values, I get 120 Kelvin. That means the temperature before the expansion is 120 Kelvin. And similarly, I know P2 V2, N2 and R. If I again apply the ideal gas law, from that I get the temperature is equal to 76.1 Kelvin. You can see T1 is equal to 120 Kelvin, T2 is equal to 76 Kelvin. Because the temperature has been dropped because of this expansion. Why? Some of the energy contained in the system has lost to the surroundings in the form of work. So that is why the temperature, as initial temperature is 120, which is higher than the T2, which is 76.1 Kelvin. So I have tabulated the values P1, V1, T1, P2, V2, T2. Okay. I hope now you understand what is the adiabatic process, and you have to digest the concept of adiabatic systems, because we are going to apply in future to the more concepts. Thank you very much. I will come back with a new lecture.